On a cold November night, a deep dish of steel stared into the dark and waited. The crew at the ground station knew the schedule. If the math was right, a whisper would cross the gulf, skim the high desert air, and thrum through a cable into a room lit by small screens. Hours passed. The dish kept its quiet posture. Then a thin bar of green appeared on a monitor. Lock. A signal had arrived from a machine no one has touched for decades. Picture the scene. The antenna is so large you could drop a stadium into its bowl. Its shadow slides over scrub grass. A red light flickers in the control room. Somewhere beyond the planets, a probe the size of a piano bench turns its weak transmitter toward home. Between the pulse and the reply lies a long delay, almost a day each way. Every note has to survive the emptiness, and every note matters. The first clear packets say little, then a pattern emerges. The craft reports that the edge ahead is not a gentle fade, it is a sudden step. The counts bounce in a narrow band, as if the probe has crossed a line drawn with a knife. On our side of that line, the wind from the sun blows outward. Outside, the neighborhood pushes back. That is not the transition we expected to find. We had pictured a shoreline of mist. We met a wall. A second surprise rides on the same transmission. Mixed into the status words is a tone, a steady ringing that does not care about distance. It hums at a pitch no ear can hear, but the instruments can. It is as if the dark itself is singing one long note. The frequency holds steady week after week, month after month. A storm from the sun may pass. A shock wave may ripple the counts. The note continues. We built models for a different story. Those stories said the boundary would be broad. They said the medium beyond would be thinner. They said turbulence would smear the handoff. The probe shows a border that acts like a hard slab, and a region beyond that seems denser. Did we draw our map with the wrong pens? Or did we misunderstand the forces that set the shape of our home in space? At the station, the engineers check the numbers twice. They test for faults. They trace each cable. They rotate the dish to rule out interference. The pattern persists. The craft is not failing. The space it swims through is behaving against our expectations. When the wind from our star weakens and the external pressure rises, the line moves like a tide. When a solar blast arrives, the line shudders. The boundary is not a place, it is a behavior. Before we go farther, touch the human scale of this. A person sits at a console and sips cold coffee. A printer chatters out strips of paper with timestamps. A small ring on a hand reflects the green from a status light. The data is late by tens of hours, yet it feels live. That small hum on the screen is the farthest continuous sound we have ever collected. It is no glitch. It is the environment itself speaking in its simplest mode. Stand with me at the rim of a dry lake where the ground antenna rises. The bowl is pointed low. The stars near the horizon have a faint smear. You can almost draw a straight line from your eye. Along the dish, through the night, and out to the machine. Our planet is turning. The operators will hand off the track to another site before dawn. The chain of listening will not break. We are shadowing a traveler beyond the planets, and it is telling us our border is sharp and alive. At the far end, the traveler drifts through a medium of sparse particles and stretched lines of magnetism. The craft is small. It has no fuel to spare. Its heat is a slow decay from metal bricks tucked inside. Yet with a whip of wire and a patient receiver, it has found the pitch of the surrounding ocean. That pitch sits near a few thousand cycles each second. It glides a little. Then it returns, like a tuning fork you refuse to stop. Here is the paradox that starts this film. Our solar system ends in a knife edge, not a fog. And just beyond that edge, the quiet is not empty but vibrating. If the border is so abrupt, what holds it in shape? If the vibration is so persistent, what pumps energy into the dark? Why does density rise where our models said it should fall? Where does the wall end? And what new walls lie beyond it? At its core, this is a story about how a thin stream of radio energy, launched by a machine lit by a distant sun, can redraw our sense of home. A boundary is not a line on a textbook diagram. It is a struggle between two breaths, the outward one from our star and the inward one from the broader environment. A tone is not a soundtrack. It is a mode in which charged particles sway. Those facts alone should change how we picture the neighborhood of our world. Imagine a tower on the frontier, not a stone tower, but an instrument tower, a watchtower of wires, plates, and logic built to notice small things. The tower looks both ways. One face watches the sun's temper, the other listens for the slightest stir in the medium beyond. When the sun sighs, the tower feels the push. When a distant region twitches, the tower hears the ring. We have posted that tower at the last breathable step of our star's reach. You might ask why this matters to life back here. If the border moves, storms in space follow different roads. If the region outside is denser, fast particles find new paths into our system. If a long tone persists, it might serve as a ruler. We can measure how the environment changes over years and decades. We can compare different directions. We can test ideas about how stars carve cavities in the galaxy. Each of those outcomes has a human link, from satellite safety to the chance of future travel. The probe did not reach this place in a straight run. It climbed past giant planets that bent its course and wound its clock tighter. It threaded a corridor of hazards we rarely speak of. Dust grains, weak fields, cold. It now coasts in a level of darkness we can barely imagine. Yet it is no ghost ship. It is a reporter. It points a simple set of ears at the void and gives us a daily line on what the void is doing. You can hear the structure of that void in the way the tone changes after a solar shock washes over the boundary. The pitch rises briefly. Then it relaxes. The delay between the shock leaving the sun and the pitch change at the frontier encodes a distance. The amount of rise encodes the stiffness of the medium. With enough events, you can map a cross-section without ever sending a camera. In this map, the colors are notes, and the notes make a contour. This is not the picture we teach to children. We show a light sphere around the sun and say, "Here are wind rules." And beyond this line, another wind rules. The truth is harder and more beautiful. It is a living contact surface. It wrinkles. It flexes. It grows thin and thick. It knows about storms before we do, because it is where the storm arrives at last. Tired and broad, with long arms that shake the whole membrane. The proof of a hard edge sits in other readings the probe relayed during its crossing. Abrupt changes in particle counts, quick flips in the way charged bits spiral. A lull in one set of streams and a rush in another. The sensor logs show it like a set of steps on a staircase. 1 second you are on one level, then you place a foot. The next second you are on a different level. There is no miles-long ramp between, there is a threshold. We must be careful with our words. The craft is not outside gravity's grasp, far from it. The sun still holds the ship in a very long leash, but the atmosphere of particles that flow outward has given way to the common medium between stars. That is the hinge of the story. On one side, gusts from our star shape the weather. On the other, the wider galaxy sets the tone. In a lab, you could build an analog. A tank of water meets a tank of syrup at a thin barrier. You tap one side, and ripples pass through the gate into the other side, changing speed as they cross. The frontier in space is like that, but with far lower density and a scaffold of magnetic lines. Tap the sun with a burst, and a reply arrives at the ship long after, in sound rather than sight. There is a social element in this tale as well. A generation launched the craft. A different generation maintains the watch. Teenagers who read about the launch now have silver in their hair. People retire from the network and return as teachers to train those who were not born when the probe left Earth. In a quiet way, this is a story about commitment that outlives careers. What does it say about us that we keep listening? If a border can be so sharp in a place with so little matter, what does that say about borders nearer to home? Do we expect slow fades because we live in air and water? What other sharpnesses have we missed because we assumed nature prefers gradients? Could there be other hard fronts in the galaxy where one domain ends and another begins? How might those fronts shape the birth of stars, or the flow of radiation, or the routes we could one day fly? The hum deserves its own pause. It is a clue and a clock. It tells us the medium has a natural frequency, a way it likes to ring when poked. It also drifts so slowly that we can compare one year to the next and feel the long swell of the environment. If the tone stubbornly remains when the ship travels onward, that says the region past the border is not chaotic. It says there is order in the darkness. Return to the dish for a moment. The structure hums softly with motors as it tracks the sky. The rigging creaks. The control room door opens and closes with a faint click. Lines on screens build into ribbons. Ribbons into curtains. Curtains into a strange but legible weather report for a place no camera can see. The station hands off the lock to a sister site across the world, and the flow continues without a gap. The traveler never knows which ear is listening, only that someone is. Now tilt your mind to scale. The ship is smaller than a car. The sphere in which the sun breathes is wider than the orbits of the giant planets. The cavity around that sphere may span hundreds of light years. The probe has stepped from one domain into another and announced the step with a ring that could double as a yardstick. That is the crux. The smallest of tools has revealed the largest of rooms. Some will ask if the wall means we are safe inside a bubble. Others will ask if the wall is fragile. The answer seems to be that it is both. It turns aside some streams and admits others, depending on conditions. It is not a castle keep. It is more like a skin that thickens and thins. When our star is loud, the skin pushes outward. When the surroundings press, the skin retreats. The ship is tasting the push and pull. In everyday language, the probe has left the wind of our sun and entered the breeze between stars, and it hears that breeze singing. That is why the instrument matters. It reduces a wild environment to a trace on paper and a tone in a speaker. With traces and tones, we can compare, we can forecast, we can correct the maps we hand to the next generation. Listen once more to the cadence in the control room. A murmur of voices, a pencil tapping, a chair rolling back. The operator calls out a time. The supervisor marks an event. They both know that no one will see the frontier in a window. They will not print a photograph and pin it to a corkboard. They will mark a spike on a plot and argue about what it means. And that is enough. Because meaning lives in relation, not in spectacle. The traveler itself offers no poetry. It is tired. It conserves power. It turns slowly to keep its thin antenna pointed home. Yet the poetry is there in what the readings imply. A wall that is not supposed to be a wall. A hum that should have faded but did not. A map that asks for a new legend. When the smallest facts break an old picture, they do not whisper, they ring. This is the opening riddle. Why does the border act like a solid skin? Why does the medium beyond hold a steady pitch as if it has a favorite way to vibrate? What larger structure squeezes our frontier into a sharp shell? Which cycles in our star or in the region beyond make the line drift? Are we sitting inside a cavern carved long ago? And if so, what left the mark? We will not answer tonight. We will prepare to chase the answers. We will take the hum as a guide and the moving wall as a path. We will let a patient instrument show us how to turn sound into distance and distance into structure. We will thread the story through a larger map of the space around our sun and ask who built that map and when. Enjoy Evidence First Space Films. Like and subscribe to the Quiet Universe channel. Next, we place the wall under a magnifying glass and test the push and pull of the sun's breath against the pressure outside, in the fence of solar wind. Imagine the sun as a restless lung, exhaling a breath of charged particles in every direction. That breath has been flowing for billions of years, filling a sphere that stretches far beyond the planets we know. It is thin, invisible, and fast. but it carries the signature of our star. Every second, a stream of protons and electrons spills outward, carving a cavity in the galactic medium. That cavity is where we live. The outer edge of that cavity is not drawn in ink, yet the Voyager probes have found it. The edge is alive, pulsing and folding like a tide that does not care about seasons. It is what scientists call the heliopause, but a better name might be the fence of solar wind. It is the surface where our sun's breath stops ruling space and begins to negotiate with the wider galaxy. The craft approaching that fence does not see in color or texture. It feels through its sensors the pressure of particles, the rhythm of waves, and the turn of magnetic lines. When the count of fast protons suddenly falls and the count of slower cosmic particles rises, the probe knows it has crossed into a different domain. The transition is sharp, almost surgical. No soft blend, no fading gradient, just a step. The image surprises even the team that predicted the crossing. They had expected turbulence, a long zone of mixing like a surf at the shore. Instead, they found a wall that acts more like the skin of a bubble. Inside, the solar wind flows freely outward, carrying the magnetic field of our star. Outside, the interstellar medium pushes back with its own current and its own field. Where the two meet, the pressures cancel. The result is a membrane of balance, a fence that hums with tension. In plain terms, space here behaves more like a fluid than a void. The sun's wind and the galactic breeze press against each other until neither can move farther. The frontier between them stores energy the way a drum stores energy in its skin. When the sun flares, the fence ripples. When the galaxy sends a shockwave from a distant supernova, the fence quivers in reply. Consider how delicate that balance is. The sun's wind changes with its 11-year cycle, breathing faster, then slower. Each change shifts the fence by a few astronomical units, a small distance by cosmic standards, but vast in human scale. It is like the ocean tide moving the shore of an island city by hundreds of miles every few years. Every variation in sunlight, every shift in magnetic polarity, echoes across this fence. At times, the pressure from inside wins, and the boundary swells outward, giving the planets a thicker shield against cosmic rays. At other times, the outer medium pushes back harder, squeezing the bubble and letting more high-energy particles reach us. This tug-of-war writes the climate of interplanetary space. It even changes the number of cosmic rays that fall on Earth's atmosphere and seed clouds. The sun's weather and the galaxy's weather meet at this invisible fence. The Voyager data show the shape of that fence is not spherical. It is dented, asymmetric, more like a drop stretched by a current than a perfect bubble. The dent points in the direction our solar system moves through the galaxy. Ahead of us, the fence is compressed. Behind us, it trails like a comet's tail. The sun drags its breath along as it travels, and the result is a cavity that leans into the future. For decades, we thought this frontier would fade gently into interstellar space. The probe's crossing proved otherwise. It is abrupt. Particle counts jump in seconds. Magnetic field direction flips, and the wind's roar stops, as if muffled by thick glass. Even the temperature curve shifts suddenly. It is as though the probe has stepped from a warm current into an icy sea, the way a diver feels a cold layer beneath the surface. The fence is not a single wall, but a layered one. Inside lies the termination shock, where the solar wind slows from supersonic to subsonic speed. Beyond that lies a buffer region of slower flow. At its edge sits the heliopause, the true border. Voyager 2 passed through all three layers, each defined not by sight but by sound in its instruments. The sensors record plasma waves, their frequencies rising and falling as the probe moves outward. Think of it like standing near a long fence in the wind. The panels rattle, each at a slightly different pitch. The tone of the vibration tells you how tight each panel is stretched. Voyager is hearing those tones, not through air, but through fields and particles. The pitch of the plasma waves reveals how dense and stiff the medium is. Where the pitch climbs, the density increases. That is how we learned that the space outside is not thinner, but thicker than the wind inside. Why would density rise outside our solar bubble? One answer lies in the speed of the galactic flow. The interstellar gas is not at rest. It moves relative to the sun at tens of kilometers per second. As our bubble plows through it, the gas piles up in front, like snow against a windshield. Another answer lies in the magnetic fields that thread both regions. When two magnetic fields press together with opposite directions, they can trap particles at their interface. The result is a cushion that grows dense. The fence, then, is both boundary and filter. It lets some particles through while turning others back. Cosmic rays, the high-energy travelers from distant sources, are deflected or slowed as they pass the border. This selective gate shapes the radiation environment of our solar system. It explains why the flux of cosmic rays near Earth changes over the sun's cycle. A stronger wind means a stronger fence, and fewer rays slip through. The discovery of such a firm wall rewrote the way we picture our system's place in the galaxy. No longer are we simply adrift in open space. We are enclosed within a cavity sculpted by our own star. The fence marks the reach of the sun's influence and the start of interstellar society, where every star's wind meets the others. From afar, the galaxy may resemble a lace of bubbles, each one the territory of a single star, merging and colliding like cells in a cosmic foam. Standing on Earth, we cannot feel this fence, yet every satellite, every astronaut, every radio signal rides inside its protection. Without it, cosmic radiation would be harsher. Electronic circuits would fail faster, and the long history of life might have unfolded differently. The border we discovered is not just a scientific curiosity. It is a shield that allows complexity to endure. To put it another way, the sun is not only a lamp, it is also a gardener that tends its own field in the galaxy. The fence is the fence line of that field. Beyond it lies the wild plain of interstellar space, where other stars sow their winds. Our gardener's fence is old, but not eternal. When the sun cools and its wind weakens billions of years from now, the fence will shrink and finally vanish. The cavity will close, and the galaxy's breath will sweep through unopposed. For now, the fence stands. Each Voyager reading is a plank in our understanding of it. The signals travel across 22 hours of light time, a slow but steady heartbeat. Each packet adds a few more notes to the melody of the frontier. We now see that the edge of our home system is not empty silence, but a dialogue, a balance, a song between two winds. What does that mean for the future of exploration? It means that to leave the sun's domain is not a simple crossing of distance. It is a crossing of environments. Any craft that goes beyond must survive in a new kind of sea, one that hums with currents we are just beginning to chart. The fence will test our instruments, but it will also guide us. Its ripples carry news from the galaxy itself. So the next time we speak of the edge of the solar system, remember it is not a cold horizon. It is a living surface, a gate that breathes with the rhythm of our star. Voyager touched it, measured it, and showed us the real outline of our home. The fence of solar wind is the first and most enduring monument we have built in interstellar space. Next, we will follow that monument outward and ask how heat and cold trade places across it, in the hot, cold edge. When Voyager crossed the fence of solar wind, the team expected the temperature to fall. They imagined a soft fade from the warmth of the sun's breath into the cool silence between stars. Instead, the readings bent their logic. Just beyond the fence, the measured temperature rose. The plasma outside was hotter than the wind inside. Heat and cold had traded places, as if the frontier worked like a mirror that flipped energy around. That inversion began one of the strangest puzzles of the mission. How can the denser, darker, older region of space be hotter than the bubble inflated by a living star? The answer hides in the way particles exchange energy at extreme thinness. In ordinary air, molecules collide billions of times per second, evening out temperature fast. In space, A single particle might travel hundreds of kilometers before meeting another. Temperature there is not the warmth you feel on skin. It is the speed of motion of charged dust and plasma. To put it another way, the outside is cold to touch, but hot in motion. Its particles move quickly, though they are so rarefied that no object could warm by them. Inside the bubble, the wind cools as it expands, much like gas escaping from a nozzle. The faster it flows outward, the lower its internal energy becomes. By the time it reaches the edge, the once fierce solar wind has slowed and chilled. Beyond the edge, the interstellar gas, though sparse, carries waves and shocks from ancient stars. Those shocks keep its temperature high in the kinetic sense. Voyager's instruments did not carry thermometers in the usual sense. They inferred temperature from how plasma waves travel and from the spread of particle speeds. When the readings flipped, the scientists at first thought they saw noise or a sensor drift. But as both Voyager 1 and Voyager 2 recorded the same pattern at different times and directions, coincidence vanished. The edge was real, and its behavior consistent. At the microscopic level, the fence behaves like a shock front in fluid dynamics. Inside, the wind flows supersonic relative to the plasma waves. At the termination shock, it decelerates abruptly, converting kinetic energy into heat. That conversion produces a narrow zone of elevated temperature just before the final boundary. So the hot region is not beyond, but within the thin shell. Outside the heliopause, energy falls again, but the density of charged particles remains high enough that their random motions mimic heat. Imagine a swimmer diving through the surface of a lake on a hot day. The upper layer, warmed by sunlight, feels pleasant. A meter down, a cold band bites your skin. Dive farther, and you might find another layer where warmth returns, carried by currents from below. The frontier around our solar system works with similar layers, though stretched over billions of kilometers. The difference is that the warmth is not thermal to our bodies, but dynamic energy stored in particle motions. The hot edge becomes clear when a solar flare erupts. The blast sends a shock wave down the wind, carrying a pulse of compressed plasma. As that pulse reaches the termination shock, it pushes the boundary outward like a drum hit by a mallet. The local density spikes, the magnetic field tightens, and the apparent temperature rises sharply. Months later, as the wave dissipates, the readings fall back. Each pulse becomes a natural experiment, testing how elastic the bubble's skin is. In everyday language, the sun breathes, and the fence breathes with it. When the sun exhales harder, the inner region warms and expands. When it rests, the bubble cools and contracts. The hot, cold edge is not static. It beats like a pulse. If we could watch it in real time, we would see waves traveling outward, some taking a year or more to reach the boundary. Each wave adds a temporary bulge to the edge, and each bulge has its own pattern of heat and cold. This rhythm explains why the two Voyagers reported slightly different distances for the crossing. The fence was not in the same place when each arrived. It had moved, puffed by one cycle and squeezed by another. The difference, about a few astronomical units, is not an error. It is proof of motion. The wall breathes in and out across decades. Some researchers have compared the structure to a weather front between air masses on Earth. Warm air rises over cold, causing clouds and rain. At the heliopause, magnetic and plasma pressures play the same roles. When the sun's wind collides with the galactic medium, turbulence blooms. The edge becomes ragged, mixing patches of hot and cold plasma. In these mixed zones, small magnetic islands form and merge, releasing bursts of energy that keep the boundary active. Why does this matter? Because those energy exchanges shape how radiation enters our system. When the edge grows hotter, it becomes more turbulent, scattering incoming cosmic rays more effectively. When it cools, the path clears, letting more high-energy particles reach the inner planets. The hot, cold dance at the frontier influences not only our models of space, but the daily cosmic weather at Earth. In the broader sense, this pattern tells us something about stars everywhere. Each star inflates its own bubble, each bubble bordered by a similar thermal inversion. The galaxy is full of these overlapping cells, hot skins surrounding cooler cores, where they press against one another. New stars can form as material compresses along their shared walls. Our solar system's frontier is not a lonely oddity. It is one note in a vast chord of interacting bubbles. To grasp the scale, picture the sun's bubble as a grain of dust inside a cavern the size of a city. That cavern is the local bubble of the galaxy, a larger region cleared by supernova explosions millions of years ago. The inner wall, our heliopause, is like a soap film floating inside the greater shell. Heat and cold pass through in waves, telling us about both structures at once. Voyager, though built to study planets, has become a thermometer for the Milky Way's ancient wounds. At its core, the paradox of the hot-cold edge reminds us that intuition built on earthly air fails in the deep vacuum. Temperature there is not a feeling but a statistic. Hotter does not mean warmer in the human sense. The probe's instruments detect velocity spreads, not comfort. When we translate those data into a map, we find patterns more like music than like weather charts. The higher the pitch of the plasma wave, the hotter the environment. Each note adds to our symphony of the border. There is another layer to the mystery. The heating near the boundary may arise from magnetic reconnection, a process where tangled field lines snap and rejoin, releasing energy. The same process powers solar flares and auroras. In the void, it happens silently, invisibly, producing tiny surges that drift through the plasma like fireflies in slow motion. Voyager senses these as flickers in field strength, a heartbeat within the wall. On human timescales, the edge seems stable, but across millennia, the balance will shift. The sun's wind is slowly weakening as its magnetic cycle ages. Over millions of years, the cavity will contract, the hot edge will cool, and the interstellar medium will press closer. One day, the outer planets might drift through the border themselves, wrapped again in galactic air. The bubble we now call home is temporary, a breath that will one day end. Why should we care? Because this structure tells us how stars live with their neighbors. It teaches us how radiation, matter, and magnetic fields share power in the galaxy. It helps us understand the limits of habitability for planets and the reach of protective environments like ours. The frontier is not just an astronomical curiosity. It is a model of coexistence between a star and the space around it. Simply put, the hot-cold edge is the living skin of our solar system. It holds back storms yet passes whispers. It keeps our region temperate, not by walls of stone, but by balance of motion. To study it is to study the lungs of our cosmic home. Every time the tone of the plasma changes, every time the density rises or falls, we learn another word in the language that connects our star to the universe. Next, we will follow that language into motion itself and see how the wall we have drawn begins to move, fold, and breathe across the years. In the moving wall. When the Voyagers crossed the frontier, the scientists thought they had seen the last dramatic change. The instruments had entered the interstellar medium, and it seemed that nothing else could surprise them. Yet in the years that followed, the signals began to drift again. The boundary they had crossed was not fixed. It moved, as though breathing, swelling outward and collapsing inward in cycles that echoed the rhythm of the sun. At first, the movement appeared small, a fluctuation in the timing of plasma waves. Then the patterns showed a clear beat. Every time the sun released a burst of high-speed wind, the frontier shifted. The wall advanced outward, sometimes by several astronomical units, then retreated months later. It was not a rigid surface. It was a flexible membrane responding to pressure, as if the entire solar system were wrapped in a lung that inhales and exhales. The cause lies in the variable energy of the sun itself. Our star's 11-year magnetic cycle changes the strength and speed of the solar wind. During solar maximum, when flares and coronal mass ejections are common, the wind presses harder, pushing the heliopause outward. During solar minimum, when the sun is quieter, the pressure drops and the wall drifts back toward the center. The Voyagers caught this cycle in action, turning abstract models into living data. Think of the boundary as the skin of a great balloon. The sun's activity is the hand that squeezes or releases it. But unlike a balloon filled with air, the material inside this one is magnetized plasma. Its tension comes not from elasticity, but from magnetic fields twisted and stretched. When a solar storm passes through the termination shock, it sends a pulse down the magnetic field lines like a tremor down a rope. Weeks or months later, that tremor reaches the edge, and the wall moves. This motion can be tracked through subtle changes in particle counts. When the wall expands, the density of galactic cosmic rays inside the bubble drops because the thicker solar wind blocks their entry. When the wall contracts, cosmic rays flood in more easily. The difference is measurable, even at Earth, as variations in radiation levels recorded by spacecraft and high-altitude balloons. Thus, the moving wall is not only a distant phenomenon, it is felt across the whole system. In everyday language, when the sun coughs, the border ripples. The delay between the cough and the ripple tells us how far the edge lies. By measuring the time gap between solar events and changes in Voyager data, researchers can estimate distance more precisely than by radio timing alone. Each solar eruption becomes a sonar pulse, and the heliopause acts as the echoing surface. From those echoes, the team has built a crude map of the wall's position and motion over time. Sometimes the echoes reveal something stranger. There are hints that the wall does not move evenly in all directions. In some sectors, it may retreat while in others it expands. The cause could be differences in the external interstellar pressure or in the orientation of magnetic fields beyond the bubble. The galaxy around us is not uniform. Its clouds and currents squeeze the solar system unevenly, distorting our bubble like a flag in a shifting wind. The movement is not just back and forth, it can also ripple sideways. Magnetic reconnection along the boundary creates local ruptures that open and close, letting small jets of plasma leak through. These leaks may form temporary channels, funneling energy across the frontier. Voyager's instruments have recorded abrupt spikes in particle flux that could mark such openings. They are the equivalent of cracks in the wall, brief windows between two environments that normally stay apart. To put it another way, the wall is alive. It quivers under the influence of forces both internal and external. It remembers every pulse of the sun and every gust from the galaxy. Each shift stores information about both. If we could translate those vibrations into a score, it would be a duet between a star and its surroundings, played across a billion-kilometer drum. The moving wall also helps explain why the two Voyagers experienced the frontier differently. Voyager 1, heading north of the ecliptic, and Voyager 2 moving south, travel through regions of different pressure. Their timelines of shocks and hums do not match perfectly. When Voyager 2 felt a solar event pass, Voyager 1 recorded it months later or earlier depending on which side of the bubble had expanded first. This asynchrony reveals the wall's shape and shows that its motion follows the magnetic architecture of space, not the geometry of orbits. At its core, this discovery shifts our sense of what boundaries mean. The edge of the solar system is not a static border but a dynamic interface. It breathes with the same rhythms that drive auroras and sunspots. It is the largest manifestation of the sun's heartbeat. To study it is to study time made visible in space, the slow pulse of our parent star written across hundreds of billions of kilometers. Why should that matter to us? Because the wall's motion regulates how much cosmic radiation enters the inner system. During periods of expansion, radiation doses drop. During contraction, they rise. For spacecraft and future explorers, that difference is critical. Knowing the state of the wall can mean the difference between safety and danger. The moving boundary is our first shield, flexible but real. There is a poetic side to it as well. The The idea that our solar system moves within a membrane that swells and contracts connects us to the living processes of stars. Every breath of the sun shapes a frontier far beyond the last planet. The Voyagers are our distant nerves, sensing the stretch and relaxation of that cosmic skin. Through them, we feel the weather of space in slow motion. Some researchers propose that the movement of the heliopause is also linked to larger galactic cycles. As the solar system travels through the Milky Way, it passes through regions of varying density and magnetic texture. These external pressures may modulate the wall on timescales of thousands or even millions of years. The bubble might expand during passages through low-density cavities and shrink when entering thicker clouds. In that sense, the moving wall carries the memory of our orbit around the galaxy. Imagine watching this from above. If such a view were possible, you would see a faint glow marking the heliopause, expanding and contracting like the heartbeat of a huge animal. The pulse is slow, measured in years, but steady. Within it, the planet's orbit, oblivious yet protected. Outside, the interstellar medium flows around, sculpting the bubble into new shapes. The motion of the wall writes our solar system's biography in the language of plasma and field. At times, the movement becomes dramatic. When a massive solar eruption occurs, the shock front races outward, compressing everything in its path, months or years later. That shock reaches the wall, producing a sudden rise in local plasma frequency detected by Voyager's antenna. The instruments hear it as a sharp note in the cosmic hum, a sign that the wall has flinched. The note fades slowly as the boundary relaxes again. Each of these sonic tremors is a reminder that even at the edge of the sun's influence, the star's pulse is felt. The wall's motion also tells us that the heliosphere is not a closed bubble. Energy and matter cross it constantly, though in small amounts. The frontier is porous. Charged particles can slip through magnetic field lines that reconnect, and neutral atoms pass freely, carrying clues about the conditions outside. This exchange makes the wall not a prison, but a membrane, a semi-transparent veil that both separates and connects. In plain terms, the moving wall is the dialogue between our star and space itself. Every fluctuation speaks of power released, of balance sought and regained. It shows that the solar system is part of a larger conversation, not isolated but responsive. To understand that motion is to understand our place within the galaxy's constant negotiation of energy. The Voyagers have taught us that even stillness in space is an illusion. Every region, every boundary, every silence hides motion. The wall we once pictured as fixed now dances. Its waves carry messages older than humanity and longer than any orbit. Through the thin thread of radio, we are learning to listen to the pulse of the vast body that holds us all. Next, we will expand our view beyond the moving skin to the enormous cavity it guards, tracing the outlines of the chamber carved by ancient explosions inside the local cavern. Beyond the moving wall lies not open wilderness, but a larger chamber carved by violence long before the sun and its planets were born. The Voyagers have given us the first clues about its shape. The data show that the heliosphere, our sun's bubble, floats inside an even grander bubble, 1,000 light-years wide, hollowed out of the Milky Way's disk by a chain of ancient explosions. The frontier we crossed is not the end. It is the inner wall of a cavern. Imagine standing in a cathedral so vast that the walls glow faintly from distant fires. The ceiling is far beyond sight, yet you can feel the echo of each sound ripple through its volume. That is the local bubble, the cavern we inhabit. It is the scar of dozens of supernovae that once erupted in a small star-forming region near the sun's current neighborhood. Those explosions swept away gas and dust, leaving a cavity of thin, hot plasma surrounded by bright shells where new stars have since been born. When the sun entered this region millions of years ago, it inherited a rare kind of shelter, our heliosphere. The bubble blown by the solar wind expands freely in this emptiness. If the sun were traveling through denser gas, the outer wall would sit much closer. But here, The vacuum is so clean that the sun's influence stretches far, like a candle flame unbroken by wind. The local bubble acts as a secondary skin, a cosmic chamber that shields us from the denser clouds of the galaxy. The evidence for this cavern comes not only from the Voyagers, but from hundreds of nearby stars. Astronomers have mapped the absorption of light along different directions. Where interstellar gas is thin, starlight passes freely. Where it is thick, the light dims. Stitching these measurements together reveals a hollow shaped roughly like a peanut, elongated and open in two directions. The sun drifts near its center, moving through the leftover heat of long-dead suns. At its edges, the local bubble meets neighboring cavities blown by other generations of supernovae. Their overlapping shells form a honeycomb of voids and walls, a cosmic foam that extends across hundreds of light years. Each wall glows faintly in X-rays and radio waves. These glowing rims are nurseries of new stars. The pressure of hot gas from the interior compresses cooler material along the boundary, sparking gravitational collapse. The death of old stars has made the birthplaces of new ones. In plain terms, we live inside a hollow made by destruction, and that hollow has become a cradle. The very shock waves that once sterilized the region now keep it alive with creation. The sun's own birth likely took place near one of those ancient shells. Over time, it drifted into the calmer heart of the cavity, carrying its planets with it. The Voyagers are now at the outer rim of that personal bubble, tapping on the wall between us and the ancient void beyond. When we study the local bubble, we are also studying the timeline of the Milky Way's memory. The walls record the echoes of supernovae that exploded one after another, like thunder rolling through a valley. Their combined blasts cleared out matter, lowering the density inside to 1,000th of the galactic average. Yet the temperature remains high, millions of degrees, maintained by the slow leakage of energy from the outer shells. The result is paradoxical, a space both hot and empty, thin yet bright in invisible light. How do we know the sun sits within such a chamber? We can trace the polarization of starlight, which reveals the direction of magnetic fields across our sky. These fields bend smoothly as if draped around a spherical void. Measurements of nearby gas clouds, such as those surrounding the Scorpius and Orion regions, show that they lie along a common surface. Computer simulations match these patterns only when the sun is placed inside a large, asymmetric bubble whose edges are lined with young stars. That geometry matches the concept of the local bubble. Voyager's readings confirm this from a different angle. The interstellar medium outside the heliopause has properties consistent with the interior of a hot bubble: high temperature, low density, and strong magnetic fields shaped by distant shocks. The probes are sampling the air of the cavern itself. Each packet of data we receive from them is a tiny bottle of that ancient atmosphere, drifting back across light hours to our antennas. The scale is almost impossible to grasp. From one wall of the local bubble to the other is about 1,000 light-years, meaning light takes a millennium to cross it. The stars that form its perimeter, Antares, Spica, and the bright young cluster of Scorpius Centaurus are the new inhabitants of its shell. Between them lies the vast empty floor where our sun floats. The cavern is so large that our entire solar system would vanish as a speck against its inner wall. Inside this structure, the Milky Way's magnetic field threads like faint smoke. These invisible lines guide cosmic rays and shape the paths of interstellar clouds. The cavity itself may not be spherical, but stretched into a tunnel that connects to another bubble above the galactic plane. Some call this opening the local chimney, a route through which hot gas escapes into the galaxy's halo. If the metaphor holds, our solar system sits in the central hall of a house with many corridors, each leading to a different neighborhood of the galaxy. The local bubble also gives us perspective on our long-term environment. As the sun continues its orbit around the Milky Way, it will eventually exit this cavern and enter denser regions of gas. When that happens, the heliosphere will shrink dramatically, exposing the planets to stronger cosmic radiation. Life on Earth will likely have evolved or ended by then, but the event will mark a new chapter in our star's voyage. Every few tens of millions of years, the Sun crosses different interstellar clouds, changing the shape of its bubble and the flow of cosmic energy around it. Why does this matter now? Because the local bubble helps explain the pattern of star formation near us. Observations show a ring of young stars surrounding our region, as if tracing the outline of an ancient wound. That ring, sometimes called the Gould Belt, sits right on the rim of the bubble. New observations suggest that many of the brightest young clusters are linked by this shared heritage. We are living inside the echo chamber of their ancestors' deaths. At its heart, this discovery turns the story of space from static to dynamic. The galaxy is not a quiet sea, but a boiling network of voids and walls. Stars explode, carve holes, and their remnants compress gas into new stars. Each generation inherits the structure left by the last. Our own sun is part of that chain, a late flicker in a long rhythm of detonation and renewal. The Voyagers, still transmitting from the edge of our bubble, are our first instruments to touch the echo of those ancient waves. Simply put, we have learned that space is sculpted by memory. The cavern around us is both monument and machine. It records the energy of dead suns while fueling the birth of future ones. When we look out and see the soft X-ray glow that fills the sky, we are looking at the faint light of the bubble's inner heat, a radiance that has persisted for tens of millions of years. If we could fly outside and look back, the Milky Way's disk would appear pockmarked with similar hollows. The local bubble is just one among hundreds. But for us, it is the whole neighborhood. It shapes the cosmic weather that reaches Earth, filters the background radiation that our telescopes read, and defines the stage on which our star performs its part. To map it is to locate ourselves not only in space but in history. The concept of the local bubble also reframes our idea of interstellar travel. A future probe leaving the solar system will not immediately enter the dense galaxy, but will wander within this same cavern for thousands of years. Its instruments will taste the sparse, hot plasma of this bubble long before encountering another wall. Interstellar flight begins not with crossing to another star, but with exploring the room between shells. One might ask, if supernovae made this void, are we in danger from future blasts? The answer is both comforting and sobering. The nearby massive stars that remain, such as those in Scorpius Centaurus, will indeed explode one day, but most are distant enough that their direct radiation will not sterilize Earth. Their energy will instead reinforce the bubble, clearing it further and perhaps reshaping its outline. Even destruction can act as maintenance in a universe of cycles. So when we picture our solar system drifting through this grand chamber, we should imagine a lantern inside a cave of smoke. The lantern's glow barely touches the walls, but the walls respond, reflecting waves that reach us as faint signals. The Voyagers are listening to those reflections now, translating the silent pulse of the local bubble into frequencies we can measure. They are hearing the architecture of the galaxy itself. Next, we will listen closer to that hum and trace its steady rhythm through the thin air beyond the wall. In the long hum, out beyond the heliopause, where sunlight fades into radio silence, Voyager began to hear something unexpected. The instruments registered a faint, steady vibration in the plasma surrounding the craft. It was not noise from electronics or interference from the sun. It was a tone, a low cosmic note around 3,000 cycles per second, almost constant for years. It became known as the interstellar hum, and it is the purest voice of the space between stars ever recorded. At first, the engineers thought it must be a local artifact, some resonance inside the spacecraft itself. They checked the systems line by line. Nothing matched the frequency. Then, when solar outbursts sent shockwaves outward and the hum shifted slightly in pitch, they realized it was external. The sound was the natural resonance of the plasma beyond the sun's influence. The void, it turned out, could sing. To understand this hum, we must think of plasma as a fluid made of charged particles. When disturbed by magnetic waves or shocks, it vibrates at a specific frequency that depends on its density. The higher the density, the higher the pitch. Voyager's instruments, designed decades earlier, were sensitive enough to pick up these oscillations by measuring small changes in the electric field between its antennas. Each tiny twitch translated into a fraction of a volt, a whisper in space converted to a digital trace. When those traces were plotted, the lines formed a clear band at the same frequency month after month. This consistency told scientists something profound. The region of space beyond the heliopause is not turbulent chaos. It is stable, structured, and filled with a faint background of energy. That background is what keeps the hum alive. It is the heartbeat of the interstellar medium. In plain terms, what Voyager hears is the sound of emptiness under tension. The space between stars is not silent. It is strung like a vast instrument, where each region hums at its own note. The note near our sun happens to sit in the kilohertz range, far below human hearing but within reach of simple sensors. If we could speed it up by 1,000,000 times, it would sound like a continuous whistle, a tone that never ends. The hum also became a ruler. By tracking its pitch over time, researchers could measure changes in plasma density as Voyager traveled farther. When a solar shock passed the craft, the hum rose briefly, then returned to its baseline. The timing of these shifts revealed how far the shock had traveled and how the environment beyond the heliopause responded. It was like using thunder and echo to measure the size of a valley. The difference was that here, the valley was the entire solar system's cavity, and the thunder came from the sun. Some waves recorded by Voyager showed slight warbles, as if the background tone were modulated by slow currents. These modulations revealed that the interstellar medium itself breathes, carrying sound waves from ancient supernovae and galactic events. The hum is a blend of all those influences, the cosmic equivalent of the ocean's roar heard from the shore. We are hearing not one source, but the sum of many, layered across centuries. The long hum is more than a curiosity. It is the first direct sample of the physical state of interstellar space. Before Voyager, we could only guess what lay outside the heliosphere. Some theories said the medium would be chaotic and stormy. Others said it would be empty beyond measure. The steady tone proved both ideas wrong. The interstellar environment is calm, but alive. A sea of slow-motion oscillations connecting every nearby star. Why does this matter? Because it tells us about the larger architecture of the galaxy. The frequency of the hum, around 3 kilohertz, matches the plasma density expected within the local bubble, the vast cavern mapped by other observations. It confirms that Voyager is floating within that same hollow, tasting its rarefied air. Each pulse of the hum, each slight variation, is a fingerprint of that environment's texture. The tone has another implication. It suggests that the sun's influence still reaches farther than we thought. Although the heliopause marks a boundary, the solar wind's ripples can propagate into interstellar space and briefly alter the hum. The probe hears these ripples months after major solar flares, showing that communication between inside and outside continues through waves, even when particles can no longer cross easily. The fence may be a boundary, but it is not a mute one. At its core, the hum is both scientific data and existential symbol. Humanity's farthest instrument is hearing the environment directly, without mediation, without atmosphere. It is as if we have pressed an ear against the wall of the universe and discovered that it vibrates faintly with the sum of everything that ever happened. It is a revelation that the universe is not dead space, but an ocean perpetually trembling. Voyager's recordings turned the abstract into audible reality. Researchers converted the electric signals into sound waves and played them through speakers. What emerged was eerie, a wavering hiss that rose and fell like wind through glass tubes. Listening to it, one senses both distance and intimacy, as though the cosmos itself were breathing near your ear. It is not music in the human sense, yet it feels composed, balanced, deliberate. Simply put, The long hum is the voice of balance between silence and storm. It persists because the forces that shape space never rest. Waves from the sun, waves from distant explosions, and waves from the galactic magnetic field all interact, sustaining the vibration. The fact that it remains so steady means that the region around us has achieved a kind of equilibrium, a pause in the galaxy's chaos. There is a poetic symmetry in the idea that humanity, a species that learned about sound before light, has reached a place where the only sense left is hearing. The Voyagers cannot see. Their cameras were turned off long ago to save power. Yet they can listen, and in listening they continue to tell us the shape of the unseen. The hum is the last communication not from the spacecraft, but from the medium itself. Over the decades, as the power levels drop, the team at Earth knows there will come a final day when the antennas no longer detect the signal. The hum will still be there, vibrating endlessly, but we will not be able to hear it. That realization adds a human echo to the discovery. Our hearing is temporary, yet the song continues. The universe will keep playing, indifferent and magnificent. Why does the hum stay at one frequency rather than drifting wildly? One hypothesis is that the interstellar magnetic field locks the plasma into stable oscillations. Another suggests that the combined effect of distant shocks averages out into a uniform tone. Whatever the cause, the stability implies a harmony of forces. The same physics that allow stars to hold together also allow emptiness to hold a tune. In the lab, scientists now replicate these plasma waves in chambers to study their behavior. They heat gas until it glows, apply magnetic fields, and measure the resulting hum. The patterns they record mirror Voyager's signals. It is as if a fragment of interstellar space has been recreated in miniature, a pocket of the void singing behind glass. Experiments like these help decode the notes we hear from the real frontier, turning sound into understanding. The long hum also connects to other cosmic phenomena. Fast radio bursts, pulsars, and magnetars all generate radio waves in overlapping frequencies. The hum is weaker and steadier, the baseline upon which those louder events play. By comparing them, we can trace how energy travels from violent bursts to gentle background vibrations. The same universe that shouts with explosions also whispers with resonance. At a deeper level, the hum makes us reconsider what it means for space to be alive. We often define life by pulse and rhythm. The interstellar medium, though not alive in the biological sense, possesses both. Its constant vibration is a sign of balance, not decay. It is a kind of mechanical breathing, keeping time across unimaginable distances. In listening to it, we are eavesdropping on the mechanical soul of the galaxy. Back on Earth, the data reach the deep space network, translated into waveforms on a screen. Engineers adjust the gain, isolate the tone, and send it to researchers. Somewhere in that digital trace lies the oldest unbroken sound ever detected by human tools. It bridges the gulf between technology and cosmos, between intention and chance. Every click and oscillation is a direct handshake with the environment beyond our star. At last, the long hum stands as both measurement and metaphor. It measures density, energy, and motion. But it also speaks to continuity. It is a reminder that even in the farthest reaches, there is connection. The hum ties our small world to the great current of the galaxy. Next, we will follow that current forward, to the shield and the ship it protects. In the shield and the ship. As Voyager drifts deeper into the interstellar medium, it carries a fragile protection that once wrapped every world of our solar system. The heliosphere, that vast bubble of solar wind, acts as a shield against the galaxy's harsh radiation. It is not solid, not visible, but real. Its magnetic fields deflect high-energy particles and redirect currents that would otherwise strike our planets. For billions of years, this invisible armor has kept the inner worlds gentler than the space beyond. But like all shields, it is changing. As the sun ages, Its magnetic field weakens, its wind thins, and the heliosphere's reach contracts. The Voyagers, having crossed its boundary, are now watching that retreat from the outside. From their perspective, the sun's protection looks like a shimmering cocoon, flickering with solar storms. Inside that cocoon, Earth spins unaware. Outside, the galaxy presses close. The idea of a cosmic shield might sound abstract, yet it governs every climate and technology on our planet. When the solar wind is strong, it expands the heliosphere, forming a thick barrier against cosmic rays. When the wind weakens, the barrier thins, and radiation levels within the solar system rise. Spacecraft electronics, astronaut safety, even cloud formation on Earth can change in response. The heliosphere is the first climate control system ever built, and it was built by a star. In plain terms, the sun's wind is our airlock to the universe. It filters what enters and what leaves. Charged particles from distant supernovae lose some of their energy when they meet the sun's field. The result is a softer radiation environment than the one that fills the galaxy. Without that moderation, the chemistry of atmospheres and the stability of DNA might be very different. Life, at least life as we know it, depends on this balance. The Voyager's measurements of particle flux beyond the heliopause confirm the shield's strength. The number of cosmic rays outside is several times higher than inside. The transition happens within a few astronomical units, meaning that our safety lies behind a wall no thicker than the gap between Saturn and Uranus. That contrast tells us how delicately the solar system is balanced between exposure and protection. Think of the heliosphere as a ship's hull sailing through a stormy sea. Inside, the crew lives in calm air, while outside, the waves of interstellar particles crash endlessly. The hull must flex, but not break. The Voyagers are like small sensors bolted to that hull, measuring every impact as the ship moves forward. Through them, we can hear the knocks and creaks of our cosmic vessel as it travels through the Milky Way. The ship itself is the solar system, and the shield is its layered armor of fields and plasma. These layers shift with the sun's rhythm. When a coronal mass ejection bursts outward, it sends a wave that thickens the armor. Months later, the wave dissipates, and the barrier relaxes. The heliosphere is alive, constantly repairing itself against the galaxy's pressure. At the outer edge, the shield does something remarkable. It turns away most of the cosmic rays that could damage life or electronics. It does this not by blocking them outright, but by scattering their paths through magnetic turbulence. Each charged particle bends and twists, losing direction and energy. The process is inefficient but effective. Over long distances, it makes a measurable difference between inside and outside. Why does this matter to humanity's future? Because when we dream of interstellar travel, we imagine crossing into that unprotected space. The Voyagers have shown what lies beyond the shield, a region filled with high-energy radiation, where even thick metal would slowly erode. For any craft carrying living beings, the first challenge is not propulsion, but protection. We must build a second shield to replace the one we leave behind. To put it another way, the Voyagers are scouts testing the hull before the next voyage. They tell us what materials must endure, what kind of radiation storms await, and how fast damage accumulates. Their data feed the design of future probes and perhaps one day, crewed interstellar vessels. The galaxy is not empty. It is an ocean full of invisible arrows, and every traveler must learn to dodge them. The sun's shield also teaches humility. It reminds us that our survival depends on forces far beyond our control. The star does not maintain its wind for our sake. It blows because of nuclear fire and magnetic turbulence in its core. Yet that same turbulence creates the conditions for life. Just as the roughness of a coastline creates harbors, the universe does not protect us deliberately, but its structure allows protection to exist. Inside the heliosphere, smaller shields echo the same pattern. Earth's magnetic field deflects solar and cosmic particles, forming another cocoon within the suns. Even human technology continues the pattern, building spacecraft with layered insulation and electromagnetic armor. Each scale mirrors the next, from planetary magnetospheres to personal suits. The cosmos seems to favor nested forms of defense, each level shielding the one within. The Voyagers, however, have no such protection now. Their radioisotope power units grow colder each year, their instruments dimming one by one. Yet the craft endure in the raw interstellar sea, wrapped only in thin metal and the echo of the sun's field trailing behind them. That trailing field, stretched by the solar wind, still offers some residual defense. It is as if the sun's magnetic lines cling to its emissaries, unwilling to let them go. Imagine that field like threads of silk extending from the sun, thinning as they stretch. The Voyagers glide along those threads, pulled slowly by the galactic current. Around them, the density of cosmic rays is higher, but not infinite. The shield fades gradually, tapering into the larger medium. In that gradient, the spacecraft measure the handover between two domains, the protection of one star and the openness of the galaxy. In everyday language, this is where our star ends and the rest begins. The Voyagers sit at that seam, showing us what it looks like to leave home. They reveal that even at the edge of protection, the influence of the sun lingers. Magnetic fields do not stop abruptly. They fade like the last notes of a song. The line between safety and exposure is not a wall, but a fading melody. Scientists now model how such shields might work around other stars. Each stellar wind builds its own heliosphere, its own moving barrier. Some are vast, inflated by active young suns. Others are small and weak around old, quiet stars. These shields interact, overlapping and merging where stellar winds collide. The galaxy is a tapestry of bubbles, each a ship in the same current. The Voyagers have shown us our own bubble's shape. The next step is to map the others. At its core, the concept of the shield unites science and story. For millennia, humans imagined the heavens as layers of protection spheres, domes, firmaments. Modern physics replaced myth with measurement. Yet the theme remains. We are still surrounded by layers that guard us from the full force of the cosmos. The difference is that now we can see how those layers work, and we can measure their thickness in numbers instead of prayers. Why does it matter emotionally as well as scientifically? Because the image of the shield gives context to our fragility. Knowing that our planet, our atmosphere, even our star's breath are all temporary shelters changes the way we look outward. It makes exploration not just curiosity but necessity. Someday the shield will falter, and life will have to carry its own defense into the dark. In that sense, the Voyagers are messengers and models. They show endurance without comfort, persistence without return. Each year they lose a little power, yet they keep transmitting. Like candles fading in a long hallway, the data they send back are not only measurements, they are proofs of resilience. They teach that survival in the universe requires both knowledge and patience. Simply put, the shield and the ship are one story told two ways. The ship is the solar system itself, moving through the galaxy. The shield is the bubble that moves with it, molded by the sun's breath. The Voyagers ride its outer skin, feeling both the pressure from within and the pull from beyond. They remind us that protection and exposure are not opposites, but stages of one process, like growth and decay. The day will come when the Voyagers fall silent. Their tiny transmitters will fade into the same hum they once recorded. But the shield they helped us understand will continue to flex and shimmer, guarding the worlds inside. And if, centuries from now, another craft follows, it will find the edge changed but still alive, a living wall tracing the heartbeat of a star. Next, we will leave the travelers behind and look at the message they carry, the letter sealed within the dark, in messages for a distant reader. When Voyager 1 and 2 left the gravitational reach of the outer planets, their mission planners gave them one final assignment. Each craft would carry a small object, a golden record engraved with images, sounds, and greetings from Earth. It was a time capsule, a message for whoever or whatever might one day find them. No one expected the message to be read soon, or perhaps ever. Yet the act of sending it mattered. It made the ships more than machines. It turned them into storytellers. The golden record is not truly gold. It is copper coated with a thin layer of gold, meant to survive micrometeorite impacts and cosmic radiation. Etched into its surface are instructions, diagrams showing how to play it and where it came from. The record holds 90 minutes of audio and 116 images encoded as analog signals. There are greetings in 55 human languages, music from Bach to Blind Willie Johnson, sounds of nature, and a single heartbeat recorded from a young woman in love with one of the scientists who built the mission. The decision to include such a record was both sentimental and scientific. The team knew the odds of recovery were near zero. The Voyagers will pass within a few light years of another star, only after tens of thousands of years. Even then, the chance of interception is infinitesimal. But the message was never about probability. It was about perspective. To send a message outward is to admit that the universe might listen and that we are worth hearing. In plain terms, the golden record is our calling card left at the edge of the map. It says, "This is who we were. This is what we sounded like. This is what our world looked like under sunlight." It is a gesture of hope written in metal, a way of saying that intelligence once lived here and tried to make sense of the sky. Imagine that distant reader, perhaps a civilization orbiting another star, perhaps something that evolved from non-biological matter. They find a small craft tumbling through their region, a relic from a dead system. They examine its worn plating, decode the diagrams, and discover the record. They hear the laughter of children, the crash of waves, the music of a string quartet. Would they understand it as communication or as art? Would they know what water is, or clouds, or wind? The act of imagining this encounter forces us to view ourselves as data. We become patterns on a disk, vibrations in a groove. The golden record reduces humanity to its essentials and reveals both our beauty and our fragility. It shows that to communicate across the stars is to simplify without losing meaning. Even a single heartbeat can say more than volumes of text if the listener knows how to feel. The record's cover carries another message, one meant to locate Earth. Using the positions of 14 pulsars cosmic lighthouses that blink with precise regularity, the diagram triangulates our star's position in the galaxy. The concept is brilliant and dangerous. Anyone who can read it would know exactly where we are. Yet the team accepted that risk. They reasoned that any being capable of finding and decoding the message would already have the technology to find us by other means. There is humility in that reasoning. It acknowledges that we are the young ones, the newcomers, the students still learning how to read the cosmic language. Sending the golden record is less an announcement of strength than an admission of curiosity. It tells the universe we are not silent and that we understand what it means to wait for a reply that may never come. The irony is that the record may never outlive its vessel. The Voyager's power sources will fail, their transmitters will die, and eventually interstellar dust will erode their surfaces. Yet even if the inscriptions fade, the idea will remain. Humanity's need to communicate across time and space is as durable as any metal. The act of sending the message already changed us. It forced us to define what matters enough to preserve. Why does this matter scientifically? Because the golden record transforms a mission of physics into a mission of meaning. The Voyagers were designed to study magnetism, radiation, and plasma. But through the record, they also study us. They carry the control sample of our culture into the largest laboratory of all, the galaxy. They test not instruments, but identity. If we think of the heliosphere as a ship, then the golden record is the logbook. It lists who was aboard, what we knew, and what we hoped for. Each track of music, each spoken word, is a coordinate on the map of our collective imagination. When future generations listen to the digital copies on Earth, they are not hearing the past, but measuring how far our thoughts have traveled. The message also echoes a pattern found throughout evolution. Life on Earth has always sent information outward: pollen drifting on wind, spores on tides, radio waves through vacuum. The golden record is simply the latest stage in that pattern, the first seed cast beyond our planetary garden. It is less about being found than about learning to plant something that can endure the cold between suns. At its core, the record is not only for aliens, it is for us. It asks what we would say if we had to explain ourselves to the unknown. It makes us think about the difference between what is universal and what is local. Mathematics may be universal, but music is human. The pulse of a heart is both biology and metaphor. In those grooves, art and science share one voice. There is something almost sacred in the way the record was mounted on the spacecraft. Each sits on the bus of the craft like a medal on a soldier's chest. Etched beneath it are the names of the engineers and the trajectory of the mission. The disc is protected by an aluminum cover, etched with a stylized atom, symbolizing hydrogen, the most common element in the universe. Hydrogen is our greeting word, the simplest hello imaginable. Simply put, the golden record is a mirror turned outward. Whatever finds it will see a reflection of the species that made it. The images and sounds may seem primitive, but they capture the essence of curiosity. They say that we looked up, built tools, and tried to reach beyond our small sky. They say that we believed knowledge could cross even the longest silence. As the Voyagers continue their slow journey, the records remain quiet. They do not transmit or glow. They simply ride along, spinning gently as the spacecraft rotate to keep their antennas aligned with Earth. For billions of years, they will wander the galaxy, passing near stars that have not yet formed, gliding through dust clouds that may one day become new systems. In that sense, they are already part of the cosmic story they set out to record. One day, long after the sun has cooled and the planets have changed beyond recognition, those two tiny messengers may still be drifting. The civilizations that sent them will be gone, but the records will remain as fossils of intention, even if no one ever reads them. Their existence proves that we once tried to speak across eternity. That fact alone is enough to make the effort worthwhile. And if by chance a distant reader decodes the grooves and hears the faint echo of human music, they will know that somewhere, once, there was a species that loved to listen, to question, and to dream. The sound of that discovery will join the cosmic hum, blending with the plasma waves until the boundary between message and medium disappears. Next, we will follow that echo into its final reflection, where meaning becomes memory and distance becomes time, in Act 3. The Voyagers have left the realm of the sun, but in truth they have not left us. Their faint transmissions, delayed by nearly a day, are the last thread of conversation between humanity and its own creation. Each signal is an echo of our voice thrown against the fabric of time, returning from the dark with a whisper that says, "Still here." The story of these ships is more than an account of exploration. It is a mirror of who we are when distance strips away comfort. Voyager carries no pride, no agenda. It drifts and listens. What it sends back is a record of attention, a study of how silence itself can teach. Through it, we learn that the universe is not only vast, but responsive. It gives answers, not in words, but in patterns of light and vibration. For half a century, the Voyagers have been our outer senses. Their journey shows that curiosity can outlive the bodies that created it. When they were launched, the world was smaller, divided by politics and limited by analog machines. Now, as they pass into interstellar night, everything has changed except the desire to know. The ships remind us that knowledge is not an achievement, but a direction. In plain terms, these probes are our fossils in motion. One day, they will be the oldest human artifacts in existence, still intact, while the cities that built them crumble into dust. They are time machines traveling forward, not to revisit the past, but to preserve it. They carry the evidence that we once looked beyond survival and reached for understanding. The distance they have traveled is measured not only in kilometers, but in self-awareness. As we followed their path outward, we discovered the walls that frame our cosmic house, the fence of solar wind, the hot and cold layers of plasma, the moving wall that breathes with our star, and the vast local cavern carved by ancient fires. Each layer taught us that borders are not ends, but relationships between pressures. Even the long hum beyond the wall is a kind of dialogue, a voice that never stops. The Voyagers show that the unknown is not empty. The silence of interstellar space is filled with meaning once you learn how to listen. What we once feared as void becomes a field of slow-motion waves and faint energies, subtle yet persistent. It is like standing inside a cathedral of invisible sound. Every motion of a star, every breath of magnetic field, resonates somewhere within it. If there is poetry in this, it lies in the unity between the smallest act and the largest consequence. A human hand tightening a bolt on a spacecraft decades ago set in motion an echo that now travels between stars. Every transmission that leaves Earth extends that echo. We speak into the universe, and though the reply is long in coming, we know it will arrive in its own form. At its heart, the Voyager mission has always been an argument against despair. It began in a time when war and doubt shadowed the horizon. Yet its goal was simple and defiant: to learn. To send a piece of ourselves outward without guarantee of return is an act of faith. That faith does not require belief in destiny or rescue. It rests instead on the quiet conviction that truth is worth pursuing even when no one is watching. The golden records attached to each craft embody that conviction. They are not just messages to hypothetical listeners, but reminders to ourselves that knowledge is not complete until it is shared. The greetings, the music, the sounds of rain and laughter, all stand as proof that the need to communicate is older than language itself. We may not know who will hear them, but we understand the urge to speak. Why should we send such a message into a void that may never answer? Because the act of sending transforms the silence into potential. It turns emptiness into context, chaos into continuity. The moment the first waveform left our antennas toward Voyager, the universe became a little less indifferent. We claimed nothing, but we joined the conversation. At its core, the legacy of the Voyagers is not about distance, but attention. They teach us to notice the small signals buried in noise, the faint hum that reveals structure, the pauses that shape meaning. Listening to space is an exercise in humility. It forces us to admit that understanding comes not from dominance, but from patience. Imagine, centuries from now, another intelligence finding one of the Voyagers adrift. They might not decode the record or even recognize its purpose, yet they would see that the object was built with precision, symmetry, and care. From that alone, they would infer that somewhere in the past, there were beings who valued beauty as much as survival. The discovery of care is as important as the discovery of fact. The Voyagers will not last forever. Radiation and collisions will eventually erode them. Even the golden record will lose its shine. But entropy cannot erase the idea they represent. The notion that life, when it reaches consciousness, seeks to explore, to preserve, and to express, is likely universal. In that sense, Voyager is not only ours, it is an example of what intelligence, anywhere, might choose to do when faced with the unknown. Simply put, the probes have shown that exploration is not a conquest, but a form of listening. Every new boundary crossed has deepened rather than diminished mystery. The more we learn about the edges of our home, the more those edges expand. The Voyagers have not answered the question of whether we are alone. Instead, they have made the question more profound by showing that we are already participants in a larger system of motion and sound. There is a deeper symmetry here. The ships move outward, while their signals fall inward to us. That inward echo mirrors the way thought moves through time. Every question we ask reaches into the future, and every answer that returns reshapes our past. The Voyagers embody that cycle. They are both question and response, evidence that even a small civilization can project its curiosity beyond its lifespan. We are left with a paradox that defines our age. The farther our machines travel, the smaller we seem in scale, yet the greater our capacity for meaning becomes. The universe does not grow smaller when we understand it. It grows more intricate, more alive. The humility that comes with knowledge is not defeat, but a recognition of belonging. We are not apart from the universe. We are one of its ways of knowing itself. One can imagine, in the far future, the Voyagers drifting through another cloud of gas, their surfaces worn, their inscriptions half eroded. Perhaps a faint current of plasma will strike the metal and make it ring once more. A tiny echo in the cosmic hum. No one will hear it. Yet the vibration will mean that a trace of our effort still exists. In that moment, we will still be speaking. As the faint radio link continues for now, each bit of data that reaches Earth is a heartbeat from the edge of our reach. It says, the experiment continues. The shield still breathes. The galaxy still sings. And as long as we listen, we are part of that song. If there is one lesson from the Voyagers, it is that the frontier is never only physical. It is also internal. To explore the cosmos is to explore consciousness. To learn what it means to be aware in a universe that can echo awareness back. The Voyagers have shown that understanding is not a boundary, but a bridge, and that the bridge is built from attention, curiosity, and hope. The probes will fall silent, but silence is not the end. It is the next medium. Somewhere beyond their last transmission, the hum will go on. The particles will still dance, and new voices will rise to listen. The story will continue because curiosity itself is immortal. And so the question that remains is the simplest and the oldest. When our echo finally fades, who will be left to listen? And what new story will they send into the dark?